Looking at our quadratic function, we're going to start doing some transformations on these different types of equations. Before we can transform them, we need to remind ourselves what is the parent function. So here's your equation, y equals x squared. Remember the x values we like to use for this one. -2, -1, 0, 1, and 2. Remember, you square the x, so if I square -2, that's going to be a 4, 1, 0, 1, and 4. I could graph these. Remember, it starts here at 0, 0, 1, 1, 2, 4. And then we have the property of symmetry for this graph. So you're going to have the same points reflected on the other side. Again, I could put the point 39 on here if I wanted to. There might be some cases where it actually helps out. There's our parent function. Remember, the domain for our parent function is going to be all real numbers. Range is going to be y is greater than or equal to 0, or if you prefer, from 0 to infinity. Different things that we can do to this equation cause different transformations on our graph. This first one, by adding a negative in front, we get a graph that looks like this. What's happened to this graph compared to this graph? This one has been reflected over the x-axis. That's going to happen every time when you have this negative in front. When you add a 2 to the inside, in the parentheses, you're going to get a graph that looks like this. What's happened this time? Notice the entire graph from this one to this one has been shifted over to the left 2. Specifically because of this part of the equation right here. Having that 2 on the inside makes it go 2 units. Left because it's a plus. Now that's kind of backwards from what you would think. So do you want to take a guess what this one's going to do? The -2 this time moves it to the right 2. So like I said, right 2. That's a little backwards from what you think. The minus goes to the right, the plus goes to the left. For our outside, an x squared plus 2. That's going to take all of these y values and add 2 to them. When I do that, that transforms our graph by moving it up 2 units. So the nice thing about this one, it kind of does what you would think it should do. A plus 2 is going to go up 2. A minus 2 is going to go down 2. Oops. When you have a number in front, and I'll tell you, these are probably the trickiest things that are going to happen. A whole number in front is going to be a vertical stretch. A fractional number, or a number less than 1, I shouldn't say fraction, a number less than 1 is going to be a vertical shrink or compression. I'm going to say shrink, but it could also be a compression. Okay? What does this mean? If there's a 2 in front, it is going to double all of my y values. So my first point here, if I double, usually it's at 0, 0. If I double the y, well, 0 times 2 is still 0. But when I get ready to do my next point, 1, 1, I double my y value. So it's going to go up twice as much as it normally does. Same thing for my next point is 2, 4. It's going to go up twice as much as it usually does. So we'll be at 2, 8. Typically, I like to make a table and kind of recreate my values. It helps me keep track of them. You remember the symmetry here allows me to kind of do this other side without actually calculating it, but be really careful. Sorry, that's not my best graph. Vertical stretch. Notice that this graph is a lot skinnier than this one because you are vertically stretching the graph. For a vertical shrink, you're going to do the same thing except you're going to half. You're going to go up half as much. So if my first point is 0, 0, and I go up half as much, I'm still at 0, 0. But my next point is usually 1, 1. I go up half as much, I'm going to be at 1, 1 half. 2, 4 will turn into 2, 2. Again, I could do my other points. If I wanted to continue, usually it's the point 3, 9. But if I went up half as much, I would be at the point 3, 4 and a half. Just to kind of get a little better picture of this little short graph. Notice when you do a vertical shrink, your graph gets wider than it usually is. So be careful thinking wider and skinnier. The terms we're looking for here are a vertical stretch and a vertical shrink. Now in this class, we are not going to have a horizontal stretch or shrink, but later on, like when you take pre-cal, you could. So again, this is more in general. So anytime you have a negative in front of a graph, and you could have some other things too, but if that negative is there, that is going to reflect over the x-axis. A plus inside the parentheses is going to move us to the left, however many units. In this case, h. A minus inside the parentheses is going to move us to the right, again, h units. A plus k is going to move us up, k units, minus k down, k units. For the A, that's when we're looking at our vertical shrink or stretch. Specifically, it's going to shrink when that A value is between 0 and 1, and it'll stretch when A is greater than 1. Now notice I didn't say anything about A being negative. If A is a negative, that reflects your graph. That's the only thing the negative does. So when we're talking about our shrink or our stretch, we're just looking at actually the number that's there. What is that? Is it between 0 and 1? Then you have a shrink. If it's bigger than 1, you have a stretch. If it is 1, then you have no change. So let's look at a couple more examples that have a few more transformations on them. So one thing I like to do very specifically is I like to start off by identifying all my transformations. A negative is going to reflect over the x-axis. Again, in this class, we are not going to reflect over the y-axis, only the x, but it's good to know that you are reflecting over the x-axis. Minus 3 inside the parentheses, remember, it's going to move us right 3 units. The plus 1, up 1. So sometimes I like to go ahead and fill out my original table of values. And then I like to make my changes based on what's in front of here. If there's a negative there, then I know that these are going to all turn negative when I reflect it. Or you could just reflect it without having to do your new table of values. So I'm going to do each of these points on its own. 0, 0, right there. I'm going to move it right 3, 1, 2, 3, and up 1. That's my new 0, 0 point. From there, there are a couple of ways to think about this. You could look at each point individually. My next point is usually 1, 1, but it's been reflected, and then I'm going to move it right 3, and up 1. Now sometimes that can get a little tedious, so one thing that I like to do is I like to call this point my new 0, 0, and then just sketch what I know the parent function looks like from there. So again, if this is 0, 0, usually we'd be at 1, 1, but it is reflected, so it would be right here. Our next point is usually at 2, 4, but again, we have reflected it, so 2, down 4. Same thing on my other side. So two ways to think about this. You can either find each point and move them individually, or you can find your new 0, 0 and sketch what you know the graph should look like from there. Either way. What is our domain for this function? Well, domain, remember those are our x values. Domain for our parent function is all real numbers. So no matter how I transform this, the domain of the transformed function is still going to be all real numbers. Typically our range is y is greater than or equal to 0. But we have reflected it, and we moved it up 1. That's going to make it y is less than or equal to, because we reflected it, and then 1 because we moved it up 1. Those transformations that affect the y values are going to be the ones that affect your range. Remember, you could write this using interval notation. Looking at our next function, a 2 in front is going to be a stretch. Plus 4 is going to move it left 4. Minus 2, down 2. So again, I'm going to fill out my values over here just like I always do. I'm going to fill out my y values. Oh, 4. That's just a 4. I shouldn't copy what's above there. I know what these numbers are. But when you have a 2 in front, remember that stretches all of these y values. So I'm going to take each one of these times 2, times 2, times 2 to figure out how far away my new y values are going to be. So that's an 8, that's a 2, 0, 2, and 8. Again, there are multiple ways to do this. This is just kind of the way I like to do it. So again, I'm going to start with 0, 0. It's still 0, 0. That's right here. But I'm going to move this graph left 4 and down 2. Put a dot. From here, the way I like to do it is I like to call that my new 0, 0. So I'm going to plot the rest of my points. Usually it's 1, 1. This time it's going to be 1, 2 because we've stretched it. Then usually it's 2, 4. This time it's going to be 2, 8. Again, because of the stretch. I could also do my points on the other side, again, because of the symmetry of this graph. It's kind of nice. And I get this equation. Domain, again, all real numbers. Doesn't matter how you change your x values, all real numbers is still all real numbers. Range is usually y is greater than or equal to 0. That's still going to be greater than or equal to because of the 2 is not negative, so y is greater than or equal to. The minus 2 moves all that down 2, so it's going to be greater than or equal to a negative 2. Again, you can see that on the graph. If you prefer interval notation, looks like that. The next couple ones, they tell you how they want you to transform this, and you need to write the equation. So 3 units to the left and 6 units down. Remember, left is inside the parentheses, down is outside the parentheses. So parentheses x. Left is a plus, so plus 3. I have to put the squared because that's the type of equation I'm graphing. And then the 6 units down, minus 6. Same thing for the next one. Reflected over the x tells me I know I'm going to have that negative in front. Stretched by a factor of 3 tells me a 3 in front also, and then just my parent function x squared. Shrinking by a factor of 1/2 tells me y equals 1/2. 3 units right, 2 units up. Again, right is inside the parentheses, so I need to open parentheses there. Right is a minus 3. Again, squared because it is a quadratic. And then up is a plus 2. Several transformations on this next one. We are going to reflect and stretch by a factor of 2. Go 2 units right and 3 units up. So again, reflect means negative. Stretch by 2 means you need a 2. 2 units to the right tells me I need something inside parentheses with my x. Right is a minus. Again, I have to put my squared because we are talking about a quadratic. 3 units up plus 3. The last way we could ask you about transformations is we could give you a graph and ask you to write the equation from this graph. Well, you should be able to do that using your transformations. I know that this is a quadratic So I know that I'm going to have some kind of equation that has x squared in it. Using this point, that's our vertex for a quadratic, or our 0, 0 point. It used to be at 0, 0. Where has it moved from this point? Well, it looks like it has gone right 1, 2, 3, 4 units, and up 1, 2, 3. It has also been reflected. One other thing we need to check is the stretch. To check your stretch, what I like to do is just check my next point. I know normally from 0, 0, the next point is 1, 1. This point is still 1 unit away and 1 unit up or down, so it's still just 1, 1 away. There hasn't been any kind of stretch or shrink done to this graph. If these are the transformations that have been done, what does that make my equation? Well, I know y equals, reflect tells me a negative in front. Again, right 4 tells me I need something inside the parentheses. Right is a minus. I need my squared because we're talking about a quadratic, and up 3 is a plus 3.